Hello everyone. In this video we're going to do a little introduction into propositional logic. So a proposition, since we're doing propositional logic, is a statement that is unambiguously true or false. So just to make sure we're all on the same page with what this means, let's look at an example and a non-example. So first, an example. The word doctor has 4 letters. So this is a proposition. It is a false proposition, of course, because doctor has 6 letters, but the fact that we can definitely assign it a value true or false means that it is a proposition. On the other hand, the statement chess is easy is neither true nor false, right? Or at least not in a consistent manner. Some people might think it's easy, some people might think it's not. A lot of people are going to have very different definitions of easy. So this is ambiguous. This is not a proposition. So now that we feel hopefully more comfortable with just what a proposition is, let's look at some things we can do to form new propositions. Okay, so not, and or are operators that we can use to make propositions into new propositions or to combine propositions. So first let's look at not. So we use this symbol to write not P, or we'll call it the negation of P. And all this means is that it has the opposite truth value of P, right? So if P is true, not P is false. If P is false, then not P is true. Okay, so now let's look at and. So here we put a little wedge between our two propositions P and Q and just say P and Q as a new proposition. And this new proposition P and Q is true if and only if both the proposition P and the proposition Q are true. And lastly, we have or. So again, we have this like wedge but going the other direction. And we say P or Q here. And this statement or this proposition is true if and only if at least one of the two propositions P and Q is true. So it's like an exclusive or here. You only need one of them to be true for the or to be true. And it's also true if both happen to be true. So now we're actually going to translate these into truth tables. Okay, so the statements that we just made to define these things, we're just going to translate into truth tables. So again, we start with our propositions P and Q. We know with 2 propositions, each with 2 possible values of true and false, we have 4 possibilities or 4 cases. And the nicest way to write out the truth table is like this, right? So the case that P is true, there are 2 cases for Q. The case where P is false, there are 2 cases for Q. Okay, so if P is true, then not P will be false. And if P is false, not P will be true because it has the opposite truth value. So you just kind of look at this column and this column and just flip T and F, right? For P and Q, this one is only true if both are true. So we see that if both are true, this is true. Otherwise, at least one of them is false, so it does not satisfy P and Q. So this is only true in the one case. And then for P or Q, we just need one of them to be true, but again, at least one. So, if we have both of them true, absolutely. And if just one of them is true, still works. And so the first 3 are all true, and if both are false, P or Q happens to be false. So we can really view these statements as being these truth table values. And so if we look for like an equivalent statement, we can always compare to these 3 columns here. All right, so now we're going to look at an example kind of putting these ideas together. So we have an or statement here that also includes a negation or the not symbol. So let's look at a truth table to kind of evaluate this, P or not P, okay? So it's a good idea to just kind of include everything that's involved in the statement, so both of the things on either side of the or, and then the whole statement itself. So we care about the last column, but we'll get there by using the first and second. So P is going to be either true or false, right? And then the negation then just flips the truth value. And we see that in both cases, at least one of them is true, and so the or statement is also going to be true. So here we have a statement that is always true. And so a proposition that is always true is what we call a tautology. And in this case, it's one that should make sense, right? Like if a proposition is something that can either be true or false, and there's no ambiguity, well, this is saying at least one of those is true. It's either true or it's false. It's exactly the same statement. And so this is a tautology. So now for your first exercise, I want you to write the truth table for P and not P instead of P or not P, and see what you figure out about P and not P. So the last thing we're going to cover will be DeMorgan's laws. So these tell us how to negate propositions such as P and Q and P or Q. Okay? Because you might look at it and think, okay, can I just distribute this and through, or the not through? And it turns out it's actually rather close, but you have to flip these. So this is equivalent to not P or not Q, and the negation of P or Q is not P and not Q. So let's actually think about this with a real world example and see like why this should make sense. So if we consider the two propositions P, I like math, and Q, I drive a red car. These are both propositions. I definitely know the truth values of these. So let's think first, what does P and Q say? Well, it just says, right, put them together with an and. I like math and I drive a red car. It's the same as true if both of these are true and otherwise is false. So if we slap a negation on both sides, what is this going to turn into? So the real world statement here would be like, it's not true that I both like math and drive a red car, right? And so what makes this true? If you don't do both things, that means at least one of them has to be false, right? So if one must be false, then that means I either don't like math or I don't drive a red car, or maybe even both, right? But at least one of these statements must be true, and, well, that's exactly not P or not Q. Of course, it turns out that I do like math, but I do not drive a red car. So the last thing we're going to do here with this statement is look at a truth table. So again, P and Q looks like this. It's only true in the first case when both are true. So if we're looking at these two statements, you know, we claim that they're equivalent. So the last two columns should have the exact same truth values. So let's see if that's actually the case. So not P and Q is easy. Once we have P and Q, right, we just flip all of these. So true, false, false, false becomes false, true, true, true. And not P or not Q means that we're looking for at least one of P and Q to be false. So here, both are true. So this is false, right? In the other cases, right, like not Q is true when Q is false, so this is true. Not P is false here, and then both are true in the last case. And so we see that the last two columns are equivalent, and so the statements or the propositions are equivalent logically. And finally, for your second exercise, we're just going to look at DeMorgan's other law there. So I want you to write the truth table for the negation of P or Q and answer this real world question. So if you ask someone if they had ham or turkey for dinner and they say no, what can you conclude from this statement? And if they say yes, can you conclude that they had turkey? All right, thank you for watching.